To further understand Faraday's law of induction, we will now consider Lenz's law. The minus sign, we talked about it earlier, but said we'd wait until we got a little further before we explained it. Well, the minus sign basically is Lenz's law. It is so important that that minus sign has a name. It tells us that the direction of the induced EMF in a current loop is such that that current produces a magnetic field that resists the change of flux through the loop. This comes from the law of the conservation of energy. So before we were just trying to calculate the magnitude of EMF. Now we're actually going to put a direction on it. Basically, if you have the external field which is being applied gets weaker, you are generating an EMF that generates a current. This current's direction will try to replace the missing external field. So if the external field gets weaker, the current will flow in such a direction that it will try to increase that external field. If the external field gets stronger, the induced current will go in an opposite direction, create a magnetic field opposing it. Now, here's the key part. Only the magnetic field within the loop counts. Disregard the magnetic field outside. Now it's time to explain the minus sign in Faraday's law. This minus sign is so important it has its own name, Lenz's law. This minus sign tells that the direction of the induced EMF in a current loop, remember, a changing magnetic field will induce a current. What's of interest to us now is which direction does a current go? So this tells us, the negative sign says that this resulting current will produce a magnetic field. Remember, a current has a magnetic field about it, and this will resist the change of flux through the loop. This is a consequence of the law of the conservation of energy. For example, if the external magnetic field gets weaker, the current is going to flow in such a direction that the magnetic field it generates will try and replace that extra field. If it gets stronger, the induced current will oppose the external field. And here's a key point right here. Only the magnetic field within the loop counts. Disregard the magnetic field outside. Let's go to some examples now. The last slide was a little tricky, so let's see if we can better illustrate the point with some pictures. Let's start with a current carrying loop here, and we have a magnetic field coming from somewhere else, and the magnetic field is coming out of the page. That's why it has the dots. And let's say over time this magnetic field decreases to 0, so you can see there's no magnetic field there anymore. Well, since the magnetic field changed, Faraday's law of induction says an EMF will be generated and a current will flow now in the loop. But which direction? So what Lenz's law is telling us that the changing magnetic field will induce an EMF in the loop that will generate a current, and the answer here is counterclockwise direction. Why counterclockwise? Well, let's draw this counterclockwise here. When we use the right-hand rule, we see that the magnetic field inside the loop is coming out of the page. And by the way, outside the loop, it's going into the page. But we don't care. We're just considering the magnetic field inside. So we lost the external field, and as we were losing it, current started flowing, and the current flowed in a counterclockwise direction to try and replace the field that was lost. Here's another example. In this case, we have a current carrying loop and with no magnetic field. Then we will gradually increase the magnetic field and note that it's coming out of the page because it's dots. We know this will induce a current in the loop, but which direction? Well, in this case, we know that the current magnetic field, it's increasing, it's coming out of the page. The current generated will try and oppose that increase. So how do you oppose something coming out of the page? You generate a magnetic field going into the page. In that case, using the right-hand rule, you find that the current has to go clockwise, generating a field within the loop here, going into the page, which will try to counteract this increasing field out of the page. Here are some tips to help you use Lenz's law to determine which way the current will flow, the induced current that is due to the changing external magnetic field. And you do it by analyzing what the magnetic field due to the induced current is going to do. Well, it will point in the opposite direction to the external magnetic field if the external magnetic flux is increasing. it will point in the original direction of the external magnetic field if it is decreasing, because it tries to prop it up, and it will be 0 if the flux is not changing. And it is 0 because of Faraday's law. There is no induced EMF if the magnetic flux is constant. And now remember, we've been talking about two magnetic fields here. One is the external applied magnetic field, and the other is the magnetic field that will be generated due to the induced current. Those are two separate magnetic fields. Here's an example of where you might have seen Lenz's law in operation. Let's say you unplug an appliance that is running, for example, a light that is plugged into the wall, and you decide to just pull the plug instead of the light. Well, hopefully this will show you why that's not such a great idea. Here's the plug, and let's see, we have wires over here, and we connect this to a light bulb. And instead of turning the light off properly, we decide to pull the plug. What happens here, as you pull the plug out, the current, of course, decreases because it's going to go to 0. You're breaking the connection. However, as that magnetic field is collapsing, going to 0, the power source in your wall, which is coming from your electric utility, will attempt to boost that magnetic field by increasing its current. So now as you're pulling the plug out, this increased current that's resulting from Lenz's law will jump the gap because it's strong enough to cut through the insulation of the air and give you a spark. Sparks are never good. So this is one of many reasons why you should always turn off appliances before you unplug them.